Hello everyone, my name is Shizhen Zhao. I'm currently a tenure-track associate professor from Shanghai Jiao Tong University. I did this work when I was working in Google together with my colleagues. We focus on cloud data centers in this work. Here is what cloud topology looks like. We have server blocks and span blocks deployed as data center modules. Inside a server block or a span block, there are many small electrical packet switches interconnected with copper cables. Between server block and span block, because these blocks may be located far apart, fiber is typically used for interconnection. As you can see, the entire cloud network can be built with cheap commodity switches. For any source destination pair, there are multiple passes, making it highly reliable to network failures. Further, cloud topology is non-blocking. This also makes routing simpler. Because of these nice properties, cloud has been widely deployed in commercial data centers. Commercial data centers have a critical requirement, fine-grained expansion. What is fine-grained expansion? Remember that there are server blocks in cloud data centers. Each server block is actually a deployment unit for data centers. Fine-grained expansion means expanding data centers at the granularity of a server block. Then, why fine-grained expansion is important? Why can't we just double the size? The reason is that deploying large amount of capacity at once incurs significant opportunity cost. For example, we may leave large capacity idle. It may stop you from using new technologies in the future because the capacity has already been deployed. Okay, we have talked about clouds and fine-grained expansion. The problem is, it is very difficult to do fine-grained expansion in cloud topology. What are the challenges of fine-grained expansion for cloud topology? First, during expansion, we may need to change topology. Remember that different span blocks and server blocks may be located far apart. In order to change topology, we may have to move fibers around. Second, the classical cloud topology was not designed for fine-grained expansion. Fat tree is a very popular example of clouds. In order to achieve full bisection bandwidth, it can be only built at very limited sizes. For clouds, there actually exists a way to construct topology for arbitrary network sizes. However, the problem is, after adding one server block, you may have to change all network links. The third challenge is we need live expansion. We cannot take the entire network offline in order to do expansion. Data centers must be highly available. No packet loss is allowed. To solve these challenges, our contribution has two parts. From architecture point of view, we introduce a layer of patch panels to better handle fiber movements. We also proposed a multi-stage pipeline for hitless live expansion. From topology aspect, historically, cloud topology was designed by hand. We developed a new computational approach to design cloud topologies with minimal changes during expansion. Our solver reduces the average number of expansion stages by more than 3x. We first talk about physical architecture. Initially, span blocks and server blocks are connected directly. Now, we introduce a layer of patch panels. Instead of connecting server blocks and span blocks directly, we connect both server blocks and span blocks to a layer of patch panels. Let us give a closer look into a single patch panel. It has front side and the back side. The first half of the front side connect to server blocks, and the second half connect to span blocks. If we use a jumper on the back side to connect two ports, we actually create a link between server block and span block. The benefit is that when we change topology, we do not have to carry fibers around the data center floor. We can simply move jumpers on the backside of patch panels. With patch panel, data center expansion becomes much easier. Here is a rough pipeline. Suppose we want to expand the data center with one server block and one span block. First, we connect the new server block and the new span block to the patch panel layer. Then, we compute a new topology. Next, we change topology in multiple stages. In each stage, we only modify a subset of patch panels. In this way, we can ensure sufficient residual capacity during expansion. In each stage, we need careful sequencing to avoid the packet loss. Before changing topology, we first need to inform our SDN controller to route traffic around the patch panels to be rewired. Then, we can ask hardware ops people to rewire patch panels. This is a labor-intensive step which can take a few hours. After rewiring, we need to test topology correctness, link quality, and many other things. If something is wrong, we need to ask hardware ops people to fix the problem. If everything looks good, we can inform all the SDN controllers that the topology has been updated. Then, the routing controller can start routing traffic through these patch panels again. Now, we get a working pipeline for data center expansion. But this is not ideal. The problem is that expansion may take too much time. First, as we mentioned earlier, each stage takes considerable amount of time. The reason is that the rewiring step is manual and could take a few hours. Second, we may need multiple stages. The general rule of thumb is that the higher the traffic, the larger the number of stages. Before we propose our solution, previous solution rewire almost all the links. That means if max linearization is 90%, then at least 10 stages are required, which makes expansion extremely slow. Actually, this is also the motivation for our minimal rewiring solver. Then, the question is how to minimize rewiring. A naive solution is that we can break some links from existing blocks using heuristic ideas, and then connect these freed ports to the new blocks. The problem of this approach is that the new topology would become highly imbalanced, which may lead to very poor performance. There were some optimization-based approach to minimize rewiring for expansion. However, none of them considered patch panels. Second, none of them have ever tried to optimize their algorithm complexity. Due to these considerations, we propose minimal rewiring, an integer programming-based approach to compute data center topology. In our formulation, we use D, M, and K to represent the total number of links connecting server block M, span block N through patch panel K. The objective function is to minimize the total number of links to be drained during expansion. There are two sets of constraints. The first set of constraints are physical constraints. Take this simple topology for example. The total number of links between patch panel 1 and the server block 1 is just one link. Then, in patch panel 1, server block 1 can connect at most one link to the two span blocks. The physical constraint should also hold on the span side. The second side of constraints are topology balancedness constraints. One example is that the total number of links from a server block should be evenly distributed among all spines. This set of constraints ensure high bandwidth for Clos topology. However, the problem of integer programming is its complexity. In our data center, the number of server blocks, span blocks, patch panels are all in the order of 100. In total, there would be 1 million integer variables. That's actually a huge scale. Actually, we did an experiment. We generate about 4,500 expansion cases. About 70% of them cannot be solved, even if we run our solver for a few days. In order to solve this challenge, we propose block aggregation. The motivation is that there exist many homogeneous components in data centers. For example, in this figure, server block 1 and server block 2 are similar, span block 1 and span block 2 are similar, span block 3 and 4 are similar. If we combine these similar blocks, we would obtain an aggregated data center topology with much smaller size. In this way, the complexity of our minimal-rewiring solver can be significantly reduced. For rigorous, in our paper, we have a detailed proof showing that the aggregated solution is decomposable. We actually propose two decomposing algorithms. One is based on integer linear programming. The other one is based on mean cost flow, which has polynomial complexity. Now, let us look at the performance. We synthesized a large number of different configurations. Each configuration has 256 patch panels and a mix of server span blocks with different radiuses. The total number of server blocks ranges from a few to 80. This is to emulate production data centers. For each base case, we do two types of expansion. One is adding a new server block with 256 uplinks. The other one is upgrading 256 uplink server blocks to 512 uplinks. We evaluate expansion using three different metrics. First, success rate within a certain deadline. This metric directly determines if our algorithm is usable or not. Without optimization, the success rate is below 30%, which is definitely not acceptable. The second metric is rewiring ratio. It is the direct metric for minimal rewiring performance. We are also interested in the number of expansion stages required for expansion. This is the direct metric for expansion speedup. Let us first look at success rate. We simulate three strategies. First, no aggregation. Second, we aggregate all layers. We use integer linear programming to decompose server span layer and use mean cost flow to decompose patch panel layer. Third, we again aggregate all layers, but this time we decompose all layers using mean cost flow. Let us look at this figure. The x-axis is the number of server blocks. The y-axis is success rate. As you can see, If there is no aggregation, the success rate quickly drops as data center sizes increases. The same thing happens for strategy 2. The reason is that using integer linear programming for decomposition is still very expensive. Note that we set the deadline of the first 2 approaches as 3 hours. Even if we increase the deadline to a few days, we still cannot see improvement. The third strategy is decomposing using min-cost flow. Min-cost flow is a polynomial algorithm. Now, even if we reduce the deadline to 10 seconds, the success rate is constantly 100%. We next look at the rewiring ratio. The x-axis is the number of server blocks. The y-axis is the average rewiring ratio. Although the first 2 strategies have much higher computational complexity, whenever they give a solution, the solution is pretty good. In contrast, the third strategy has low complexity, but gives much higher rewiring ratio. I would not say its performance is bad, because wiring 20% of links is already much better than rewiring all the links. The takeaway message from these simulation results are as follows. First, the block aggregation can significantly reduce algorithm complexity, but it may incur suboptimality in terms of rewiring. Even if we have block aggregation, decomposing using integer linear programming is still very expensive. The min-cost flow decomposition algorithm runs very fast, but incurs additional optimality loss. Now we are facing a dilemma. If you can't wait, you can use the fastest algorithm, but you get suboptimal solution. If you can wait, maybe you can get a better solution, but this is not guaranteed. In order to achieve a balance, we implemented a parallel solver. We just launched multiple solvers with different strategies, set a deadline, and pick the best solution from the finished solvers. Using this parallel solver, let us look at how many expansion stages we can save. Before minimal rewiring, every time we do expansion, we have to rewire all the links. If we rewire in 4 stages, roughly 70% of the original bisection bandwidth can be maintained. With minimal rewiring, the number of required stages can be significantly reduced. This table tells us how many cases require 1 stage, how many requires 2 stages, or even 4 stages. Here, if a solver fails to produce a solution, we assume 4 stages are required. As you can see, parallel solver has the least number of required stages. If we do some math, the average number of stages is actually 1.29 for parallel solver. To conclude, we first demonstrated the importance of using patch panels in data centers, which has been generally overlooked in the literature. We then proposed, implemented, and tested minimal rewiring solver for data center expansion. This is the first algorithm that deals with patch panel constraints. This algorithm is also highly scalable with our optimization technique. Overall, our minimal rewiring solver reduces the average number of expansion stages from 4 to 1.29, which corresponds to 3.1 times reduction for expansion time and labor cost. That's all for my talk. Next, I will hand off to Jeff to help answer any potential questions.
Okay, we'll go ahead and applaud. All right, so if there are any questions for Xingang via Jeff. I think maybe one thing I'll ask just to kind of start things off is that you know, the focus of this talk is very interesting in that you are kind of incrementally upgrading and expanding a network while it continues to operate.
Yeah.
And I mean, I remember even in the 90s, computers, desktop computers had various upgradable CPUs and upgradable caches and all these things. But as sort of speed went on, eventually you just started having integrated devices where you didn't upgrade remotely. Do you think there's some point where there's going to be a kind of a incremental decrease in the benefit of upgrading versus just replacing?
Well, I think the problem is that at the scale of 100,000 server networks, you just can't afford to turn off the network and replace it. As Shizhen pointed out, these networks last for a long time. There's multiple technology generations during the lifetime of a network. And so we want to be able to amortize the cost of the hardware over many, many years while we're introducing new things. And we also don't want to build it out to its full size initially because that's a lot of wasted equipment and capital. So, I think the fact is that we've learned sometimes the hard way that it's actually possible to do these live expansions without too many failures. So the important thing is that the frequency of failure is in some ways related to the number of wires you move, and it's not totally that. And so reducing the number of wires you move around, patch panel wires you move around, is actually very important for that too.
Okay, great. And then maybe, Ming, setting up your laptop, I have just one other question, which is, so this last problem of avoiding physical rewiring and human error was sort of the promise of 3D MEMS switches and all these companies that sort of developed devices in the early 2000s and late 90s. Have you thought about doing that instead of these manual patch panels?
Well, you know, I think first of all, the patch panels are relatively cheap. That helps. I think the other thing is that unless the switch is hitless, you know, with an electrical packet switch, when you change the forwarding table, you don't lose any packets. But with an optical switch, even very fast ones, you're going to lose some packets. And so even although the time constants may be different, you'd still like to be able to minimize the number of times you do that. Any other questions? All right. Thank you.